Okay, and this is section 14.4 in certain books in Pasadena, and at Cal Poly it's 14.6, tangent planes and differential equations. So the homework will tell you which section it is based on the class you're taking. This is nothing new from what we know, and let me derive a few things for you. So the idea is, suppose that f has continuous partial derivatives, an equation of the tangent plane. So let's say we're looking at a plane. A surface. Let's say we have the surface S defined by z equal f of x, y. And if I take a point on it, let's say that point, on the actual surface, and I define a plane, keep in mind the only common point between the plane and the surface is this P naught. If I want to find an equation of a plane given z equal f of x, y, well, I know how to do that. Tangent plane specifically. I know how to do that. We did that in the previous section. Take z minus f of x, y equals 0. Find the gradient applied on this. So the gradient of f would be actually negative f sub x, negative f sub y, and 1. And 1 times z minus z naught, assuming the point is x sub 0, y sub 0, c sub 0, minus f sub x into x minus x naught, minus f sub y into y minus y naught equals 0. That's what we did in the previous section. Now, if I move those to the right, do you see I'll get this equation? And that might be a bit confusing to you, and let me tell you how that works. Even though your homework might not reflect what we did in the previous section, in this section, I'm going to point that out and I'm going to add extra examples. If I have z on one side equal, then I could use this all the time. But if I don't, if I have z squared instead of square rooting both sides, or if I have z appearing in multiple places, I can't get z on one side, everything else on the other side. Guess what? We did all of this. Now, the deal is, this plane right here is what we're finding. And later on, I'm going to explain the difference between the linearization, what that means, and the differentials and what that means. Based on this graph, I'm going to mimic this graph again. I'm going to try to do a better job, and then we'll see how that goes. For now, we want to find an equation of this plane, an equation of a line that's normal, right? Normal to this, well, we know the gradient is always perpendicular, so any multiple of that will be a vector that's normal to the plane, and that's all we need. So start with the example. Given an equation of a surface and the point P naught, find an equation of the tangent plane, equation of the tangent line. Now here they tell us z equal, so I'm going to do this. So a and b z equal, I could use what they have here, kind of like, sort of like y minus y1 equal m into x minus x1, if you think about it, in 2 dimensions. But I added 2 examples in which you do not have z equal. You could solve for z, but what for? We know how to do that because we did that in the previous section. And if you want to do the same here, if you want to get everything on one side, 0 on the other side, and stick with this all throughout, that's fine as well. In chapter 16, we're going to be using this all over the place. So, if I wanted to stick with what they say here. They say z minus z naught equal the partial with respect to x, the partial with respect to y. Well, let's see. If you decided to follow that, you would say z minus 0 equal, I need the partial with respect to x. Well, the partial with respect to x on that problem is really 2x, evaluated at 1, 1, 0, that is 2. And the partial with respect to y is 2y at 1, 1, 0, that's also 2. So this is 2 into y minus 1 plus 2 into y minus 1 as well. So the equation for the plane is 2, oh boy, okay, you guys know what I mean, right? 2x plus 2y minus 2 minus 2 minus 4. That would be the equation for my plane. And the reason I'm leaving a lot of space, I want to do this problem two ways. So this is I. Now, assume you want to stick with what we did in the previous section. Suppose we want to go by section 14.5. All what you have to do is make sure that you have f of x, y, z equal k. Again, this is going to come back in chapter 16. So you have z minus 2x minus 2, oh my goodness, z minus x squared minus y squared equal negative 1. And you take the gradient of f, which is negative 2x, negative 2y, and 1. Evaluated at 1, 1, 0, the gradient is actually negative 2, negative 2, and 1. So, if I want to find an equation of a plane, I could say negative 2 into x minus 1 minus 2 into y minus 1 plus 1 into z minus 0 equals 0. This equation and that equation are identical. I just want to point that out. And if I want to go for part B, let's say, or double I, now it's fairly simple. If you could read this off of this, so if we have z equal, the k component is always 1. And you have to take the opposite of that and the opposite of that. That's normally how it works. So any multiple of that will do. Again, so here I would say x equal 1 minus 2t, y equal 1 minus 2t, and z simply equal t, 0 plus. That's the equation of a line. So, important to figure out. Again, it's up to you. You want to stick and use what they have in this section, you can. You want to stick with what you know, you can. Here we do the same thing. I'm going to say, look, that's z minus 5e to the negative x squared minus y squared equals 0. And if I take the gradient of f, the partial with respect to x, that's going to be, what is that? E to the negative x squared minus y squared times negative 2x, 10x. And that's going to be 10y e to the negative x squared minus y squared. And the partial with respect to z is going to be simply 1. And if I evaluate that at 1 half, 1 half, and okay, I didn't, the z is not going to come in, right? It doesn't matter what z is because there's no z there. Well, that's going to be 10 e to the negative 1 half, 10, oh, I'm sorry, 10 times a half is 5 e to the negative 1 half, 5 e to the negative 1 half, and 1. So, an equation of my plane would be 5e to the negative 1/2 into x minus 1/2 plus 5e to the negative 1/2 into y minus 1/2 plus 1 into z minus 5e to the negative 1/2 equals 1. And that's pretty much it. That's fine. That's all you need. And if you want to use the book's technique, you could say y minus 5e to the negative 1/2. I'm stuck on y minus y1. Z equal f sub x. Well, isn't that f sub x evaluated at 1/2, 1/2? That will be 5e to the negative 1/2 into x minus 1/2 plus 5e to the negative 1/2 into y minus 1/2. And let me just check the difference here. Except here, if I take f sub x, that's going to be 5e to the negative x squared minus y squared times negative 2x. So that's going to be negative 10x e to the negative x squared minus y squared. And f sub y is going to equal, obviously, negative 10 y e to the negative x squared minus y squared, evaluated at 1/2, 1/2. That is negative 5e to the negative 1/2, and that's negative 5e to the negative 1/2. So depending what you use, this is what we did in the previous section. This is what we're doing now. It's up to you. And the equation for the line will simply be x equal 1/2 plus 5e to the negative 1/2 t. Y would equal 1/2 plus 5e to the negative 1/2 t. And z equal 1. No. Z equal 5e to the negative 1/2 t plus t. Okay. I wanted to graph one of those for you. So if I sketch a graph, let me go ahead and graph it and come back and show you really quick how this works. Okay, by graphing it, I found a mistake. This point is not on it. You let x equal 1, y equal 1. That will be 2 minus 1. Z must be 1. So I messed up on this part. So when I do this part, it should be z minus 1. And when I do this part, it should be z minus 1. So that z equal negative 3. Good thing I graphed it, otherwise I would not caught the mistake. So now if I go and look at what I have, this is the graph. And if I plot the point 1, 1, 1, it's right there. That's x and y, so there. X, y, and z, 1, 1, 1. And if I plot my equation 2x plus 2y, z equal 2x plus 2y minus 3, I'll get this plane, and as you see, that's tangent that touches at one point. If you look at it like two-dimensional, it looks like, right? So there you go. Alright, I could graph the other one, but you know those things take time, and time is something we don't have. And it could be something messy, but the calculator could graph that easily. 5e to the negative x squared minus y squared. You could do that easily on the actual graph. Z equal E raised, oops, the other E raised, and let me get rid to the negative x squared minus y y squared, and I can't remember what was there. Oh, and a 5 in front of it. And let me eliminate those. So that's what the graph looked like. And I could find a tangent anywhere on it. If I shift it up by unit, probably you'll see it better. Oops, I added 1 to the power. That wasn't my intention. I wanted to add 1 to the whole z. Plus 1. Go up. Okay, there we go. As you see, this is shifted up 1 unit. Alright? So we could find an equation and plot those. You know, you could play with those on your own time. Now, I'm gonna stop this video here and I continue in the next video. This will be like 15 to 20 minutes each.